This screencast will serve as the introduction to circuits, but on another topic, hopefully everyone made it home safely and you learned the importance of static friction when you're driving versus kinetic friction. But on that note, I hope everybody made it home safe, and look forward to seeing everybody on Friday. This will just be a 6 or 7 minute video again. We're going to talk about circuits and just get a brief introduction to the topic. So circuits are a set of electrical components connected to allow for one or more paths for the movement of charge. But getting to the point of it all, why do you guys care about this whole electricity thing? A big part of our quality of life is hinged upon electricity and really the conversion of electrical potential energy into other forms of energy that we utilize. An example from everyday life is the one thing I've never seen a student leave behind in a class. I've seen lots of calculators, sweatshirts, books, but nobody's left their cell phone. So how does your cell phone work? Well, that's pretty complicated, but to even charge your cell phone, that electric potential from the wall outlet, the phone converts that to chemical potential energy to charge that battery, and then when you're using your phone then reconverts that chemical potential energy back to electric potential to basically power the supercomputer that you have there in the palm of your hand. Almost everything you do on a daily basis would be drastically different without electricity and circuits. But what is a circuit? A circuit is a system with a voltage source and a load that are connected to allow current to flow. So to have a circuit, again, you need three things. You need a source, a load, which will be a resistor, and a closed loop to allow current to flow. The two circuits we've used in class thus far closely resemble the circuit that's drawn above. For the resistance lab, we had a 9-volt battery as our source, and then our load were those spools of wire that we used to calculate the resistance. And for the Ohm's Law lab, we had the voltage generator for the source, and we were connecting that to those resistors and then measuring the current so that you were able to calculate the resistance. But what other loads are there? And what do loads do? Loads really convert electrical energy to another form of energy. So we have light bulbs. They're converting that electrical potential energy into heat and light for us. Resistors converting that electrical potential energy into heat. And then a motor can convert into mechanical energy. Some terms you'll hear to define circuits or to describe circuits are that there's an open circuit. So what that means is that there's no path from the positive to the negative terminal for current to flow. So in the one drawn above, you can see the wire is broken, so therefore there's no path that current can take to get back to the source. The next example, the closed circuit, there's a completed path for that current to flow. So current's able to travel through that circuit. And then lastly, the short circuit. So there's a complete path with no load, which gives us a very small resistance and then a very large current. So as Mr. Davis mentioned during the Ohm's Law lab, the current is always going to go through to some of the groups. The current's going to find the path of least resistance. So in this case, all of the current would go through the short circuit. None of it would go through the resistor over here. And that would cause that battery to get very hot, those wires to get very hot because of that large current. And if this happened in your home, one of your circuit breakers would trip or your fuses would trip, and that would cause then an open circuit, so then no current would flow. But yeah, so the fuse is open when the current is too high. Two terms when talking about sources that you'll hear are electromotive force and terminal voltage. Electromotive force is the energy per unit charge produced by a battery or generator. That would be the ideal terminal voltage. So for a AA battery, it would be 1.5 volts. But then the terminal voltage is the actual potential difference across the terminals of a battery. The terminal voltage will always be less than the EMF, or the electromotive force, because the internal resistance of the battery uses some of the energy. I've drawn some common symbols that are used to describe circuits. The first you've seen is just a wire. These are the various ways that wires are drawn to show a circuit. The next one is a resistor. This is typically how you'll see resistors drawn in circuit diagrams. The next is for a light bulb. So this will just be a simple light bulb installed in a circuit. You'd see it looking like that. Batteries can be drawn really either way here. You'll see capacitors in circuits drawn with either the two parallel plates or sometimes the parallel and then the open or the C-shaped plate on the other side. And then you'll see switches drawn like this in the off position. That would cause an open circuit. And then this is the circuit or a switch being turned on. Showing a switch in a circuit, but then switch being in the on position. The two types of circuits that we'll talk about the most are going to be either series circuits or parallel. A series circuit is a circuit that provides a single path from terminal to terminal, so there are no junctions. So the example shown below, a battery and 3 light bulbs in series. So that all loads must conduct for anything to conduct. Your lights that you see around the holidays are typically set up in series, where if one of the light bulbs doesn't work, the rest of that strand of lights is not going to work. So for a series circuit, what is the current that would have been going through that L1, L2, and L3 from the previous drawing? So for all of those lights, they would have had the same current. So I total equals I1 equals I2 equals I3. That would be the current going through light 1, the current going through light 2, the current going through light 3 would all be equal. How can we find the equivalent resistance or the total resistance of that circuit? In a series circuit, the total resistance or equivalent resistance just equals each resistor added together. So in this case, the resistance of lamp 1 plus the resistance of lamp 2 plus the resistance of lamp 3. And then we can find the total current from Ohm's law, V equals IR. So I total equals the potential difference of the battery divided by the equivalent resistance of that circuit. We're going to spend most of tomorrow going over series and parallel circuits. So don't feel like you have to have a complete understanding of either series or parallel circuits as you walk into the class tomorrow. So what does a parallel circuit look like? It's a circuit that provides a constant voltage across multiple resistors. So in this case, you have our voltage source right here, positive terminal, negative terminal, the positive terminal connected to this junction, the negative terminal connected to that junction of this light bank. So the potential difference, or the voltage across light 1 and light 2 and light 3 is equal. So how would we measure so what would the current going through L1, L2, and L3 be? Well, if I is the current going through the wires there, then I total would equal I1 plus I2 plus I3. And I'll show that on the picture above. So you can see at this terminal, the total current splits and goes through lamp 1, lamp 2, and lamp 3. And those values for the current 1, current 2, and current 3 would depend on the resistances, the internal resistance of each of these lamps. And again, we're going to go through this, spend most of the day on Friday going through these parallel and series circuits. Just wanted to show an introduction to what series and parallel are and show you the symbols that we'll be working with in circuits and show those arrangements for parallel and then also for series. Well, everybody enjoy the last day off. I look forward to seeing everybody on Friday.